Welcome to note set number 9, where we're going to finish up our initial coverage of the Z transform. Obviously, we will be using it throughout the rest of the course, but this will be our the end of our explicit coverage of it as a object of interest, and it will become a tool to use. So we're going to look at a few characteristics of using the Z transform to analyze discrete time, linear time invariant systems, and see what kind of insight it allows us to get. So pay attention to how difficult it might be to try to determine these kinds of insights if all we had was, say, the difference equation and didn't have the Z transform as a tool, or we didn't all we had was convolution. So these things could be analyzed with either one of those tools, but it would be much more difficult to get the insights that the Z transform really shows. So hopefully this gives you a feeling that even though the homework and the test problems will be, mostly use the Z transform to find the output, that in the real world we don't really do that. We're just having you do that for kind of practice and experience and get used to the tool. The real world signal processing engineer thinks in terms of the Z transform, and it informs what is possible, what isn't possible, what kinds of behaviors are typical, and things like that. Okay, so this is covered in section 3.5 of the textbook. So the first thing we want to take a look at is transient and steady state responses. So we're going to be focusing here completely on the zero state solution. And so any part of the output due to initial conditions we're going to either A, ignore, or assume is zero due to zero initial conditions. So we're really only interested in the zero state solution. And that zero state solution will end up having two parts. One part will be the transient part, and the other part is the steady state response. And we talked about this in the signals and systems class, and we're going to explore it a little bit deeper here. So we start off with a difference equation that looks like this. We've got our input side, our output side, we've got our input side. And just taking a quick look at this, we can, if we think about this in the recursive form, so swinging this over to the other side, we see that y of n depends only on past outputs. So that's good. We have it in the recursive form. And if we look at these terms, for I equal to 0, we have x of n. For I equal to 1, we have x of n minus 1. And then we go all the way up to x of n minus m. So y of n can be expressed in terms of, to write out y of n, we need past outputs, and we need the current input sample, that's for the I equal to 0, and a bunch of past ones up to m. What we don't need are n plus 1, n plus 2, and so therefore we can immediately identify this system as being a causal system, because the output at y of n depends on only past outputs and no future inputs. So we can immediately tell that it's causal. We can then write out a of z and b of z. This is a little bit different form than what we had before. We haven't factored out this term out in front to handle the poles and zeros, poles or zeros at the origin. But nonetheless, this will still allow us to see what we need to see. So for this example, we'll define a and b this way, and we can then write the transfer function as b of z over a of z. And so if we assume that the zero initial condition, or that the initial conditions are 0, our zero state solution in the time domain is convolution, and therefore using the convolution property we know that the output Z transform is just a product of the input transform times the transfer function. So h of z is called the transfer function. And so since we have from a difference equation, we have this rational function for our transfer function, we can substitute that in. So this is a fairly general result. In fact, this part is extremely general. Any linear time invariant system can be written that way. This result obviously depends on the system being described by this type of difference equation such that we get a rational transfer function. But the vast majority of discrete time systems, I mean, I'm talking about virtually everyone that we'll be interested in, and even in subsequent courses and out in the real world will be such rational functions. So this is what we're going to take a look at is something of this form. So just for simplicity, it doesn't have to be. We can get to the same ideas, but just for simplicity, we'll assume that our input signal also has a rational form. And you'll see that quickly that those things kind of go away. The F sticks around, but the E just kind of goes away. And it won't be too terribly important. I could have left this as it is, but it's a little easier to see when we have this form. You could literally do a partial fraction expansion on this, and we're going to assume distinct poles, so no repeated poles. So we get a bunch of terms that look like this. If there were repeated poles, there are ways to handle those repeated poles, and we would arrive at pretty much the same insights and ideas. So we'll just assume distinct poles for right now. So the key is that when we do a partial fraction expansion, remember we're interested in expanding it out into factors that look like this, or that come from A and F. So these are all the factors that make up A. So those are the factors of the so-called characteristic polynomial A of z, which is the denominator of the transfer function. And then we would continue breaking this up into all the factors of f. And so we'd have a whole bunch of terms here that would have the factors of f in the denominator of each term. But then we could smash those all back together and get back to this this form. So let me get rid of all this stuff here. And we're just smashing all that back together because that's all we really care about. So this d of z is just going to be some polynomial that would come after we factored out all the factors for f through partial fraction expansion, and then smash it all back together to create f in the denominator, and we'd end up with some polynomial d up on the top. So then if we do a inverse transform of this, we look these things up on the table, and we see that each one of these terms gives us something that looks like this. And we see that if the poles are all inside the unit circle, that means the magnitude of p sub I is less than 1. And we're allowing these poles to be complex or real. The only thing we're not considering is repeated poles, just for simplicity. So if we have a stable system, every one of these terms will decay as n goes large. So that's why we call this part here the transient solution. It will go away after enough time. And so every linear time invariant system will have a transient part of its solution that often will go away quite quickly. If the poles are far from the unit unit circle, these transients can decay very, very fast. And then eventually they are kind of out of the picture, and all that's left is this thing. And the term that's typically used for that is called the steady state response. And I understand the choice of the term, but it is somewhat of a misnomer because students often think that it means that that the steady state must have some sort of steady characteristic to it. It can, but it doesn't have to. So its behavior depends on what these things look like, and largely what the denominators factors, the factors of the denominator f look like. So depending upon what x looks like and how it interacts with the system, this term could be rather steady, or it could also decay away by itself. And if the input is growing without bound, the steady state could also grow without bound, and that's perfectly fine. A stable system driven by an input that grows without bound will generally, not always, but could have an output that grows without bound. But the important thing is that if we have a stable system, this transient response decays away, and in control systems applications, this transient response is actually one of the most important things. It controls how quickly we can get to kind of the steady state response of the system to our control signal. So it controls, if you're you turn up the thermometer or the thermostat on your heating system, you set it to heat to a higher temperature. There's going to be a region where the temperature is going to whatever that new temperature is, and that's handled by this transient response. Eventually, the transient response goes away, and what is left is just the steady state part of it. And for the furnace and thermostat, the steady state would then hopefully, ideally, just be a constant temperature being held. So for control system applications, the transient response is of very much interest. In signal processing applications, we're usually applying a signal and then looking at what happens long after we've started applying that signal. So in signal processing applications, we're very much more interested in the steady state response. And later in the course, I'll talk about kind of ramp up characteristics of filters, and that is actually this transient response. So if you're trying to simulate a system that you're going to put some music through it, and you want to see what comes out, you usually want to ignore the transient response because it can be misleading if you look at that without looking at beyond the point where it starts to decay away. So when we're simulating things, we often will throw away the first part of the output, so that we aren't being tricked by seeing what the transient response is. So hopefully that'll become clearer as we go further into the course. So just to revisit causality and the region of convergence, we have talked about the fact that that for a causal system with the initial conditions set to 0, we can't get any non-zero output until the input becomes non-zero. That's kind of our rough definition of what a causal system is. So, and we've alluded to this next statement a few times. So since h of n comes from putting delta of n in, and delta of n is 0 up until n equal to 0, if the system is causal, there's no way that h of n can be anything but 0 for n less than 0 if the system is causal, since delta of n doesn't start until n equal to 0. So we have that idea, and then we've also seen that for a causal sequence, the region of convergence for the Z transform is the outside or exterior of a circle. So putting those two ideas together, we can see that if we look at the transfer function and the region of convergence is specified, all we've got to do is check to see if the region of convergence is the exterior of a circle. If it is, then we know that we have a causal system. And this is really nothing more than restating. We had a single slide that summarized three results for region of convergence. One was for causal, one was for anti-causal, and one was for bidirectional. So for the causal, we saw that it was the exterior of a circle. So this is just restating that in the context of an impulse response and its transfer function. So that leads us to this statement that says an LTI system is causal if and only if the region of convergence of its transfer function is the exterior of a circle. And then we get a little technical here to nail everything down. So we make sure, we assert that the circle must have a radius r that's finite, and that exterior must include the point z equal to infinity. So we've seen situations where z equal to infinity is excluded, but we can't do that here. So we now have a very simple way of looking at causality just from looking at the region of convergence of the transfer function. And so now we can talk about the impact of, or the interaction between the region of convergence and stability. So early on we saw that a necessary and sufficient condition for an LTI system to be stable is that the impulse response is absolutely summable. So the absolutely part means you take the absolute value. The summable part means is that you take that absolute value now and you sum it up, all points from minus infinity to positive infinity, and that sum must be less than infinity. If it is, then the system is bibostable. And so we can start with this input, or with this specification, and gain some insight into what this says about characteristics of the region of convergence relative to stability. So we start with our definition of the transfer function. So that's just the z transform of h of n. And now, we're interested in looking at where is the magnitude of h of z bounded. So we're working to try to bound that because that connects to the region of convergence. So we look at the magnitude of the transfer function, and then we play this trick. We played it once before. The magnitude of a sum of things is less than the sum of their individual magnitudes. And that's easy to see. Say 3 plus negative 2 must be less than absolute value of 3 plus absolute value of negative 2. So it's pretty obvious that that holds. Then we have a magnitude of a product of two things is just the product of their two individual magnitudes. So we have that. So let me clear off some of this stuff here. And so then the next thing that we have that we do here is, so we have this result that says the magnitude of h of z is bounded by this. And so now let's look at this result. This holds for all z. And so since it holds for all z, it must hold on the unit circle. So if we let magnitude of z be equal to 1, then this term goes away. And so we now get this part becomes absolute, the sum of the absolute value of h of n, and we see that that bounds h of z. So, but we've restricted it to be on the unit circle, so it bounds h of z on the unit circle. So that's what we have there. Let me clear some of this stuff off here. I wish there were a faster one swoop thing that I could do to clear them off, but it takes a couple pokes of my screen to get that done. So we now have this result, and basically for a stable system, we know that this is bounded by infinity. And so, oh, I shouldn't have less than or equal to here. That should just be less than, because this is less than, must be less than infinity. So now I can bound this strictly by infinity. So what this says is that if the system is bibostable, then the unit circle must be in the region of convergence, since I've showed that the magnitude of the transfer function on the unit circle is less than infinity. So that allows us to state the result that you learned in the Signals and Systems class. LTI system is bibostable if and only if the unit circle is in the region of convergence. That's just another way of saying is bibostable if and only if all poles lie strictly inside the unit circle. Since that condition for a causal system puts the region of convergence outside where the poles are, and includes the unit circle at that point. So that's what I'm saying here for a causal system. This should say we know the region of convergence is the outside of a circle, and that circle must be inside the unit circle. So we're illustrating it down here. The red circle is the circle defined that all the poles are inside of that, and the region of convergence is outside. So that red circle must be inside the unit circle in order for stability. And so that leads us to this idea that all the poles must be strictly inside the unit circle in order for the system to be a causal system to be bibo or bibostable. So we've now established the result that I kind of just foisted upon you in Signals and Systems, but now we have a little stronger establishment that that is actually true. So what happens if we have a pole on the unit circle? Let's take a look and see what happens. This is actually a scenario that's known as marginally stable. And we'll see that for some inputs, for some bounded inputs, the output will be bounded, but there are some special bounded inputs that will cause such a system's output to grow without bound. What we're going to do is show that we can't have a pole on the unit circle and still have bibo stability. And to do that, all we really need to do is introduce one counterexample. So proving that something holds is a lot easier than, or is harder than proving that something doesn't hold. In many cases, to prove that something doesn't hold, all you got to do is show, that there's one case that doesn't work. So let's start with a single pole at z equal to a, and we're not really saying yet where a is. And just for simplicity, we could do all this in a more general setting, but just for simplicity, because remember, we just need a single counterexample, so let's make it simple. Let a and b be real and positive. So we've got a system that looks like this. We're going to pick an input transform that has the same structure. Now we're going to let b for the input. We're going to restrict b to be less than or equal to 1, but greater than 0. So that tells us that the input is bounded. So remember, if b is less than 1, and we inverse transform this, we get a decaying exponential. If b is equal to 1, and we do the inverse transform, we get x of n is equal to the unit step. So in both cases, we have a bounded input. And so now we're going to form the output as the product of those two. So we get something that looks like this. And then we can do we can do partial fraction expansion. And if we assume that A is not equal to B, then do the inverse Z transform, we get something that looks like this. So we would do a partial fractions expansion of this, and we'd get a term for Z minus A and a term for Z minus B, and those would transform to these two respective terms. And both of those are bounded. Well, they're certainly bounded if the pole is inside the unit circle. If the pole is on the unit circle, then a to the n, a will be 1. We'll get capital A times u of n. As long as the input is bounded, which would be the case if, as we've said, b is less than or equal to 1. So for a pole on the unit circle, both of these things, both of those terms will remain bounded. So that's fine. Let me clear some of this stuff off here. And then head back. So that shows that there are some inputs for which the output will remain bounded. But let's look at one special input. Let's suppose that we have A is equal to B. So when A is equal to B, we do the inverse Z transform of this. We're going to have to do a partial fraction expansion for repeated roots. And if you look it up, you'll find out that for repeated roots we'll get something that looks like that, which is our standard form. And then we'll get something that looks like this, where we have the same exponential, but we have an n factor in front. So let me clear this off here quickly. So let's look at that. So if we have a pole that's strictly inside the unit circle, then A is less than 1, and this term clearly decays. And you can actually show that when A is strictly less than 1, n a to the n, it'll start going up. It starts at 0, obviously, because n is equal to 0. When n is equal to 0, we have that product equal to 0. And as n grows, we'll see that this term starts to go up, but then ultimately the exponential wins out, and so it starts to come back down. So that's if the pole is strictly inside the unit circle. Now, what happens if we have a pole on the unit circle? Well, then A would be equal to 1. This term remains bounded. It just becomes capital A times the unit step. But this term becomes capital B times n times the unit step. So it becomes a ramp function at the output, and so the output is unbounded. So what we've just established is that when we have a single pole on the unit circle, then there are some bounded inputs that will cause bounded outputs, but there are some special ones that will basically cause a resonance, and that's exactly what's happening. It's very much like a resonance, and that resonance will cause the output of the system, in this case, to grow without bound. And so that's why we call a system with a single pole on the unit circle. Well, any poles that are on the unit circle are single poles, not repeated poles. We would say would be a marginally stable system. And I'm just giving you a little exercise here to look at the case where there are two poles at z equal to 1. Just to see if you can analyze that and get a feeling for what's. So summarizing our results, stable if all poles lie strictly inside the unit circle. Then we say that marginally stable if there are some single poles on the unit circle, but no poles outside the unit circle. And then unstable if there's at least one pole outside the unit circle and or at least one multiple pole on the unit circle. Then the system would be strictly unstable. So this just summarizes and makes a little more precise some of the results that you saw back in the Signals and Systems class. So this talk of stability brings up an interesting theoretical issue of pole zero cancellation, and it's worth commenting about this. So, we're forming this y of z, so we could be forming, we're basically multiplying some z transforms to form y of z, and there could be a pole that is in the same location as a 0 in this function y of z. And so the question is, do they really cancel out? And yes, they do. You should cancel them out. And there's actually two ways that we could get this pole zero cancellation. So, there could be something in H that cancels something in X. So a factor in the numerator of H that cancels a factor in the denominator of X, or vice versa. But it could also happen when we start cascading a few systems together, and a pole of one is where a 0 of another is, in which case, technically, theoretically, those poles and zeros would cancel each other out. So let's take a look at a cascade of two systems. Let's say H1 looks like this and H2 looks like that, and we look at this and we say, okay, here's a pole outside the unit circle, and so therefore the first system is not stable. And then we go into a second system that looks like this, and notice that we have the same factor in the numerator. So if we look at the total transfer function for this cascade of these two systems, it's just the product of the two. And therefore, mathematically, we have a z minus 2 and a z minus 2, so we should be allowed to cancel those out. And we're left with something like this that suddenly is stable. We've got two poles, both inside the unit circle. We've got two zeros, one inside the unit circle, two inside the unit circle. But it doesn't really matter where the zeros are. So we've got a stable system. Now this way of stabilization by pole cancellation works in theory, but in practice you have to be very, very careful that when you really do implement these systems, that that the pole and zero, that the numbers that determine where the poles and zeros are, the coefficients of your system, say in the transfer function or the difference equation, when you code those into your computer, they can get rounded off to the precision of your computer. So numerical precision issues may end up in this pole and this zero not being exactly at the same place, so they don't quite exactly cancel each other. So what looked like on paper would end up being a stable system ends up being one that could be, really unstable. I should say actually unstable, and it might only be like vaguely or barely observable that it's actually unstable, but in certain circumstances it could definitely grow without bound. So you need to be aware of that. Don't rely on cancellation of poles and zeros in practice unless you're absolutely sure that it will really work. Okay, so here's a little example of how this works, where the cancellation is between the input and the output. So we've got a difference equation describing our system. We've got an input that consists of just two little, two samples, one at n equal to 0 and one at n equal to 1. We can find the transfer function. We can factor that and find out what it looks like. We can take the z transform of our input, and we'll leave everything in the z inverse form here, because we can see what happens when we take x of z times h of z. we're going to have z minus 1/3 z inverse cancel with this, so that will cancel with that, and we're left with just these two terms in the product, and that's what we have here. And so the time domain form for the output, if we do the inverse Z transform of this, we get just one mode that's happening here. We would expect there to be two different modes happening. The modes are each of the poles being raised to a power of n. So we see the response due to one pole, but not the other pole. And that's because for this particular system, for this particular input, the input kind of cancels that response of the pole. Or said another way, the input has zero value where that second pole is, and so the second pole is never really excited by this particular input. And so that can be an oddity that happens and might be hard to explain in a real world situation. So you should be aware of that kind of scenario as well. So we'll close this off. We've been talking about stability, and when we get later on into the course, we will be trying to build discrete time systems from some building blocks. And we'll be using two-pole subsystems because those are fairly easy to design a two-pole system, and then we cascade a bunch of these together to create a higher order system. So if we can design each one of these two-pole subsystems to be stable itself, then the cascade of them all to get the more complicated higher order system will be stable itself. So I'm not going to go into the details of this real deeply, but just kind of lead you quickly through the analysis and then see what the result of this is. So we start with a second order difference equation. We get the transfer function in terms of Z inverse. We convert it into the Z form of the transfer function, and then we find the poles. So we're basically finding the roots of that polynomial. So we apply the quadratic formula to find these second order poles, and so here's the result of that applying the quadratic formula. And so from this we can kind of extract the idea. We can see that if we put these things back together and do a little bit of algebra, we can actually figure out that A1 is going to actually be equal to minus the sum of the two poles, or the negative of the sum of the two poles, and A2 is actually the product of the two poles. So like I said, you can kind of work that all out by working a bunch of algebra. And so from these two results, we can then establish a few inequalities. We can show that for stability, since P1 times P2, if the thing is stable, that the magnitude of A2 must be bounded by 1, and also the magnitude of A1 must be bounded by 1 plus A2. And so these two inequalities establish a triangle, and if the A1, A2 coefficients from our difference equation fall inside this triangle, then that two-pole subsystem will be stable. And then likewise, if we look at this term here inside the quadratic, when that's equal to 0, that's the point where the quadratic goes to 0 and we have repeated roots. And that's also the dividing line between having real roots and complex roots. So if we err on one side of this equality, so if the left side is greater than 0, then we have purely real roots, distinct real roots. If the left side quantity is less than 0, then we get a negative inside the quadratic, and we get an imaginary number when we take the square root, and so we get complex roots. So solving this equation, we get this, and that equation, or that relationship, defines a curve that in the A1, A2 space that divides the region of real roots from the region of complex roots. If we look at this figure, and this is right out of the textbook, the red triangle here, the interior of that is called the stability triangle, and you can see that that's defined by this line, A2 equal to 1, and then this line and this line, which set up that inequality that relates A2 and A1. So anything inside, so we are on the A1, A2 plane, so we're looking at any point on this plane corresponds to two values, or let me say it this way, a value for A1 and a value for A2. So each point on this plane specifies a particular two-pole subsystem. And so if the point that defines that subsystem lies inside this triangle, it's stable. And then this curve, this quadratic, is the dividing line. So anything above that is going to have complex conjugate poles, and anything below it will have real and distinct poles. So we have this triangle that then is split into two parts. And so if we're trying to achieve a stable system, we must be inside the triangle. If we're aiming for real poles, we must be in the upper region, bounded by that quadratic. And if we want, I think I just said that backwards. If we want complex conjugate poles, we need to be in the upper part. If we want real and distinct, we need to be in the bottom part. So, this just gives us a way of constraining a design to be sure that it's going to be stable, which is a nice ability to do. With these systems, when we're trying to design them, if we're trying to optimize relative to some criteria, we may end up with a design that optimizes that criteria but is unstable. So we could then specify a constrained optimization, find whatever the optimization constraint is, find the A1 and A2 that satisfy this optimization constraint, yet still lie within the stability triangle. So again, not a big deal, but just something to be aware of. And we'll stop there, and I'll see you in the next set of notes.